All right, so welcome. This is the second part of Unit 1, and some of Unit 1 is really easy to review, and we did that last week. And the second part of Unit 1 is a little bit, you may have seen it in chemistry before, but in AP, it's basically called spectroscopy, mass spec, and PES. Where do we get the ideas of how many electrons or things something has? So it's going to be looking at some graphs and kind of making some decisions. And then we have our friend called the beautiful periodic trends to come back to. And that is a major thing on the AP exam. So if you want to do really well on the AP exam, kind of follow along with what we're doing now. And we'll come back to it several times as part of review sessions through A+ College Ready. And I'm sure your teachers will have lots of stuff to say. So right now you should see my screen that's got some directions about how to join the Pear Deck. Obviously, if you're watching this video later, there's no way to do this, but you can pretend. Just open up a new tab in Chrome or something like that. Type in joinpd.com and type in that lovely code DEZTH. And as soon as we've got a bunch of y'all in, we'll go ahead and start. So you have to understand that you really will have two things going on. One will be a Pear Deck presentation that you're seeing, and one will be my screen that I'm sharing. So you can kind of see what's going on. So this is the teacher side of things right now. You can see that there's four students connected, and this is me connected as a student. So here in a second, we'll go ahead and roll along. For those of you still trying to get in, I'm going to go ahead and start. But remember, you can just go to joinpd.com and you can type in that code DEZTH, and then you can see exactly what I'm seeing. So we want to go ahead and make sure you're on Pear Deck so you can interact. And we also want you to make sure that you feel free asking any questions that you have. So if you have a question, you can put it in the chat box. So in Google Meet, there should be something, if you kind of wiggle your mouse at the bottom that says chat, and you can type a question in there. And you can also unmute your microphone at any point and say, hey, I had a question, and then we'll see what you guys have. All right, so let's go ahead and get started. So we ended last time with the idea of electron configurations. Electron configurations is something that you would have done in just regular chemistry. So just as a brief reminder, we have energy levels. So the first, second, third, and fourth, and those correspond to the rows of the periodic table. Then we have sublevels. So there are 4 parts: the S, the P, the D, and the F. Then we have orbitals within those sublevels. And then we say that 2 electrons can fit in each orbital. So when we write electron configurations, we say things like 1s2, 2s2, 2p3, that kind of thing. So this is a periodic table of that shows you how many electrons there are in each part and where each part is. So you probably remember this or got taught this in chemistry. And remember, if you have questions about any of this, you can ask questions, and you can also bring it up to your teacher. So the S section is over there on the left-hand side, and it's kind of blue. And it holds 2 electrons. The P section is over there in pink, and it is 6 elements wide and holds 6 electrons. So remember, each orbital holds 2 electrons, and that means the P sublevel would have 3 orbitals. So let's take 2p6 and understand what that means. 2p6 means in the second energy level, the 2, there's a P sublevel. Within that P sublevel, there's a certain number of electrons, and those electrons get put into these things we call orbitals. So we can describe any electrons using that information. And then we've got that section in the middle. Notice that the D section is 10 elements wide. From scandium to zinc, if you counted up the boxes, you would see 10 spots. And then down there at the bottom, you've got that green section, and that's the F sublevel, and we really don't see that on the AP exam. So when we do electron configurations, really what we're trying to figure out is where are all the electrons, how many valence electrons does something have, and once you know how many valence electrons something has, you can also then go about talking about how reactive it is, and you can also go about describing where those electrons are kept and how tightly those electrons are bound to the nucleus. So this is a quick, how do we know what we know about atoms? So once upon a time, we didn't know anything about atoms, and then poof, all of a sudden we did know about atoms. So what changed? We developed things that let us understand and read certain information. So in the early 1900s, we were able to discover that there's a nucleus, and we were also able to tell that there were protons and neutrons, and we developed this thing called mass spectrometry. Not important that you know how it works, but it is important that you be able to read a graph. So we know that if you add the protons and neutrons together, we get the atomic mass number. So with the atomic mass number, you'll see in the graph on your screen that it goes from 88 to 98, and you'll see 4 individual bars that correspond to peaks. So each one of those is a different isotope. We know that isotopes all have the same number of protons, but they differ in the number of neutrons. So each one of those 4 peaks that you see in the graph represents a different isotope. The height of the peak, so how tall it is, look at how tall the one for 90 is, that tells you how abundant it is. So if you were to look at each one of those peaks and add up the percent abundance, it would add up to 100%. This is where we get the information from to calculate average atomic mass. So we took the mass of the isotope times its percent, plus the mass of the isotope times its percent, and so on and so on. So mass spectrometry tells us all about what does the nucleus look like. We also use something called PES, photoelectron spectroscopy. So we shoot X-rays at elements, and we measure how much energy does it take to knock loose electrons. So the height of the peak in this lower graph tells us something about how many electrons there are. And then the bottom axis, the x-axis, the binding energy, that tells us about how much energy does it take to knock them loose. The bigger the number, that means the more tightly held those electrons are to the nucleus. So mass spectrometry tells us about the nucleus. Photoelectron spectroscopy tells us where are the electrons and how many are there. All right, so here's one for neon. And we see 2 peaks from neon. And we can see some numbers up there in the graph. The red numbers are unimportant. The blue numbers are very important. They are the percent abundance, excuse me. So that first peak at 20 tells us that the mass number of 20 is 90.48% of all the neon that we find in the universe. And then there's one at 9, there's the one at 22 makes up 9.25%. And then there is supposed to be a little tiny peak at 21, but notice you can't even see it. That's because it's only 0.27%. It's such a small amount that you really don't see that about neon. So what we can tell from this is nothing about neon's electrons. This is mass spectrometry. We can only tell something about its nucleus. How many protons and neutrons does it have? So in Pear Deck, if you join the Pear Deck, then you should see in your Pear Deck window, you should see the ability to enter the number there. So my question for you in Pear Deck is, how many different isotopes do you see? So go ahead and take a minute. And how many different isotopes do you see? All right, so most of y'all guessed 4 or 5, and that's right. I was trying to trick y'all that it was 4, but if you'll notice, there are 5 actual peaks. There's one here at 49.17. The isotope 64, zinc 64, is the tallest one. Then you have one at 66, one at 67, and one at 68. And then if you look way over here at 70, notice there's a very tiny little bump right there, and that bump represents an isotope. And notice that it's 0.61. So again, we know nothing about zinc in terms of how many electrons. This is only telling us about the nucleus. So remember, you can look on a periodic table and look for the atomic number, and that tells you how many protons something has. And then you can go in and say, aha, I can also find the number of neutrons by taking the mass number, for instance, zinc 64. So take that 64, and if you subtract the number of protons that you find on the periodic table, then boom, you can figure out how many neutrons that is. So let's take a look at another one, see how we do. That was very good, y'all. So here's my question for you this time on Pear Deck. So keep in mind that I want to know, what is the average atomic mass for copper? Is it closer to 63? Is it closer to 64? Or is it closer to 65? Based on the graph that you see, what is the average atomic mass of copper that you get from this graph? Okay, so I'm going to show y'all what you said real quick. And most of y'all said 64, and some of y'all said 63. And I like both those answers, because those answers, I was trying to trick y'all a little bit, but basically I left it very wide open. So could it be 63 or 64? Well, if we look at the graph real quick, you'll see that the tallest peak was 63. So since that's most of all the copper, then we would estimate that the overall mass, the average mass of the copper, should be closer to 63 than it is to 65. So those of you who guessed 63 for that reason, great job. Those of you who guessed 64 because you thought, by the time I do the math, it might end up close to 64, you're right too. And notice no one said 65, which is really what I was most worried about. And if we look and see what is the average atomic mass on the periodic table, you see that it's 63.54. So basically, 3/4, 75% or 70% of all the copper is copper 63, and only 30% or 31% of the copper is copper 65. So we would expect that the copper's average atomic mass should be closer to 63. So great job for no one guessing 65. All right, photoelectron spectroscopy. Hang on a second. Okay. Photoelectron spectroscopy, on the other hand, I lost my mind for a second, tells us about the electrons. So we're not worried about protons and neutrons anymore, just about the electrons. So do me a favor, for neon, can you go ahead and find neon on your periodic table? So if you don't have a periodic table, you can pull one up real quick, or if maybe you have one with AP, you can grab that. One of my favorite periodic tables is the periodic table at webelements.com. So regardless, if you could kind of pull up a periodic table and look at neon, And what I want you to think about is how many electrons does neon have? Neon has 10 electrons because it has the atomic number 10. So what would be its electron configuration? Well, we always start with the 1s. So notice this top row is only 2 blocks wide, hydrogen and helium. So we would say 1s2, and that would be 2 electrons. Then we would say, come down to the second row, and this is exactly 2 blocks wide, and we would say 2s2. And then we'd come over here to this second row, but in the yellow section, and we would say 2p, and neon would be the 6th one over. And if you add up the 2 in the 1s, and the 2 in the 2s, and the 6 in the 2p, you will get to 10 electrons, which is what we want. So here's my question for you. Which one of those peaks corresponds to the 1s electrons? So you should have an answer choice in Pear Deck where you can say, I think this peak, the one at 84, the one at 4.68, or the one at 2.08, which one is the peak for the 1s electrons? All right, I've got some answers coming in. It's okay to be wrong. Remember, the goal is to be better at the end of this than we were at the beginning. So which ones is the 1s electrons? So let me show y'all what you put, and then we'll see. So most of y'all said, but not by a wide margin, 4.68. And then we had a little bit of the first peak and a little bit of the last peak, which is a good way of saying, in general, y'all really don't know. And that's okay. That's part of the goal, right? So how do we know how to read this? Well, this peak at 84, we know that it's 2 electrons high because there's a 2 above it. And this peak down here at the end at 2.08, we know it has 6 electrons, not only because it has a 6 above it, but because it's way higher than the other 2 peaks. So how high the peak is tells us the number of electrons. So let's think about this for a second. What attracts electrons? Well, what attracts electrons is the nucleus. So who do you think is pulled on more tightly by the nucleus? The electrons in the 1s that are very, very super close to the nucleus, or the electrons in the 2s or 2p, which are farther away? Which ones do you think are held the strongest and thus will have the highest ionization energy? And the answer comes out here, the peak at 84. So just take for a second and read those axes and think about it for a minute. What you'll notice is these axes don't look like a normal graph for us. Normally, a graph would start at 0 at this far left side, and then it would go all the way out to 100 on the right-hand side. But notice that this is a logarithmic kind of graph. They break it down to here's up to 1, here's up to 10, and here's up to 100. So you really have to pay attention to the numbers. Whoever is the closest to the nucleus is going to have the highest ionization energy. And what does that mean, highest ionization energy? It means it takes the most energy to knock loose those electrons. So you guys have probably all seen this in class before. You're sitting in class, there's a troublemaker, maybe it's you. If that teacher wants to maintain control of that troublemaker, then they put them right up front so that they're closest to the nucleus, I mean the teacher. And that teacher has the greatest effect because they're closest to the student, and there's a stronger energy kind of binding them together. So that's what we call the the binding energy. So when we talk about ionization energy, we're really talking about how far away are the electrons, and also what can you think about how many protons something has, and how does that affect the pull on all the electrons. So remember here, read the scale and make sure that you get the highest number is the closest. And then from there, you could also go, oh, this is 1s2, and then 2s2, that's the 4.68, and then 2p6, 2.08. So even without this wording that says neon up here, we can still get from it that we know that this is neon, because we can go 2 plus 2 plus 6 is 10 electrons. Look on your periodic table and figure out who that is. So this is a PES actually from in FRQ, so from a free response question on the AP exam. So on Pear Deck, you should be able to maybe try and figure out what this element is. So using what you've learned so far, go ahead and look at your periodic table and type in the symbol for the element. So let's say you thought it was hydrogen, you would just type in H. And if you thought it was, let's see, something else, uranium, you would type in U. But what do you think this element is? Take your time, write it in. I mean, look at your periodic table, take your time, and try and figure out which element this might be. Okay, so far so good. Y'all are coming in. This graph is a little bit harder because it doesn't have numbers on top of the peaks. But it is with the 45 on the left-hand side and the 0 on the right-hand side. So we do have that same number layout, just like we did in the last one. Does anybody else want to get in? All right, so let me show y'all what you came up with. So we had a neon, a nitrogen, a boron. Actually, I think I can do this. An oxygen, a neon, a helium, and a nitrogen. So 2 neons, 2 nitrogens, a boron, an oxygen, and a helium. So a little bit of everything all over the place. And the correct answer there is that it's nitrogen. So let's see if we can figure out how we do that. So this peak right here at the 40, this is where the 1s electrons go. So 1s holds 2 electrons. So the way we read this graph is 2 electrons takes up 2 lines. So since this peak goes up 2 lines, that means there's 2 electrons in it, because we know the 1s holds 2 electrons. Then this next peak at about 2.5 or 3, down here at the end, that's also the same height. And we would say that is also 2 electrons. So it'd be 1s2, 2s2, and then notice that this very last peak on the end doesn't go all the way up like it would for 6. Notice if each line is 1 electron, that last peak goes up 1, 2, 3, 3 electrons. So the way you read this is there's 2 in the 1s, and that's the first peak. There's 2 in the 2s, that's 2 more electrons. And then this last peak tells me there's 3 electrons. So 2 plus 2 is 4, plus 3 more is 7. And then who has 7 electrons? Nitrogen. So the correct answer there was nitrogen. Now, let's take a look at what it would have looked like if some of your other answers were there. Let's say it was helium. Well, if it was helium, then right here, this first peak, that's all you would see. If it had been oxygen, it would have been this peak as normal, the second peak at about 3, and then this very last peak, instead of being 3 bars high, that last peak would have been 4 bars high, because oxygen has 1 more electron, or a total of 8 electrons. So that peak would have reached up almost to the top where the green is, right? So that's how we read one of those. And let me go ahead and roll on to the next one. We'll see how we do. This is all about practice and getting better. So this one allows you to write on the screen. So for this pear deck, I'm going to let you to pick up your paintbrush or with your mouse or your finger or whatever you got. You can also do a text box. But if you would write N on one of the graphs, and if you would write O on the other one of the graphs. So pay attention to them. Which do you think is N, and which do you think is O? All right, y'all are getting in, that's good. You can notice how neatly I scribbled out the identity of the elements, because that's just how good I am. We're also going to see how many of y'all actually listened to me just a minute ago. So far, so good. You guys are getting exactly what I was hoping you were getting. So the correct answer there is yes. The one on the top is N, and the one on the bottom is O. And you can do this several different ways. The first way is to say N has 7 electrons. So 2 plus 2 plus 3 is 7. That's one way to do it. You can also write down the electron configuration. So this would be 1s2 and 2s2 and 2p3. And the way you do that on the periodic table is you go, aha, so this is 2p3. The last thing you wrote is 2p3. That tells you you're in the second row. So here, and then in the P section, so this orange part over here on my screen, and then the third one over. So 1s2, 2s2, 2p3, you would go, aha, this has 3 electrons in it right here. So that must be nitrogen, right? So those of you who said nitrogen for the first one, which is most everybody, that's great. And then you'll notice the other difference here is 2 and 2 and 4, right? So now you know what element it is. So that's great. Now, what I want you to notice here, and this, don't go drawing on it until we're ready, till I ask you the question, but this time I want you to look at the numbers for a brief moment, because I lined them right up on top of each other so you can compare them. So if you look at the 1s electron, so those are that first peak that's got the biggest number, they're the closest to the nucleus. So those are the 1s electrons. So what do you do with that information? Why is one number bigger than the other? So why does oxygen have an ionization energy down here of 52.6, while nitrogen has an ionization number of 39.6? They're both the 1s electrons. So we're not worried about, oh, well, one is 1s and one is 2s. We're talking about both the peaks for the 1s. So why would oxygen have a greater ionization energy than nitrogen? So anybody want to unmute their mic and chime in? Anybody got a clue?
Because it's further to the right of the periodic table?
Sure. I could also say because it's got the letter O in it. Both are true things, but what does it mean that it's farther to the right? Like, what does that mean to you? Just because it's farther right or farther left doesn't really give me a good explanation for why.
The nucleus has a stronger pull on the electrons because it has a greater mass.
Okay, I'm loving that. And so let's just clean up one thing. So you said oxygen's got a stronger pull because it has a stronger mass. Let's talk about what is pulling on the electrons. So how could we clean up that statement? Oxygen's got a stronger pull because it's got a greater, don't say mass, I need something else.
It has a greater number of protons.
Got a greater number of protons. Yes, because remember the neutrons are neutral. They don't pull on electrons. It's not like, you know, the sun pulling planets or anything like that. The positive charge has to attract the negative charge. So notice that the oxygen graph says Z is equal to 8, and the nitrogen graph says Z is equal to 7. And that Z notation is how many protons it has. So we would expect that oxygen to have a stronger pull on its electrons because it has more protons. So here's what I want you to draw on. If oxygen is supposed to have a stronger pull on its electrons, can you circle the peaks that seem like they don't quite agree? So pick a color and kind of circle that part on your graph that says, that doesn't really match up. There's not a trend for both of them. One set of peaks between nitrogen and oxygen doesn't seem quite right. So go ahead and take your pen and draw that in. So try to circle both of the ones you're talking about. A couple of y'all have just circled like one of the peaks. So just go ahead and circle both of them, okay? I love the fact that one of y'all crossed yours out and then did it again. That's great. If you change your mind, that's fine. That's good. Because you can always go back and erase. Remember, there's a tool down there that lets you erase. So the answer is that over here, it's that very last peak. So if we look at this very last peak right here, something seems wrong. Because the 1s electrons, oxygen should have a greater ionization energy than nitrogen. And 52 is greater than 39.6. So that makes sense. And then this one, oxygen is 3.04 for this peak, and nitrogen is 2.45. That still makes sense because oxygen here has more protons pulling on those electrons. So every peak from oxygen, we would expect to be shifted slightly over to the left from the peaks in nitrogen. But what about this last peak down here? Notice that this last peak down here, yes, they're different heights, and that's fine. But that last peak down here, notice that the numbers are slightly different. So nitrogen is 1.40. We would expect the oxygen to be greater than 1.40. And then, but we look and go, oh, it's only 1.31. So what could be causing oxygen, who has more protons, what could be causing oxygen to have a lower number there? And it really comes back to electron configurations. So let's think about what the electron configurations are for just a second. Oxygen would be 1s2, 2s2, 2p4. So if you look on my screen real quick, I'll show you on this periodic table. Remember, this orange section has 6 spots for electrons. There are 2 electrons per orbital. That means there's 3 spots in the 2p sublevel. There's 3 spots, each which can hold 2 electrons to put those electrons. So you may remember from regular chemistry something called Hund's rule. Hund's rule is just like fried chicken at my house. Everybody gets 1 piece, And then if there's seconds, then you can go back and have a second one. So nitrogen would have 3 orbitals, each with 1 electron in it. So it would have 3 orbitals, which can hold 2 electrons, but there'd only be 1 in each orbital. Oxygen would have 1 orbital with 2 electrons in it, and 2 orbitals with just 1 electron in it. So what does that mean for us? Well, electrons hate each other. Since electrons hate each other, we call that electron repulsion. So if the electrons that are in that 2p sublevel really, really hate each other because they're the same charge, then that electron repulsion will push the electrons away from each other. And if you push those electrons away from each other, it actually makes it a little bit easier to remove those electrons. So because there's that electron repulsion, that means it takes less energy on average to remove those electrons. That's why the peak is slightly to the right at 1.31, when we would expect it to be to the left, something greater than 1.40. It's this kind of thinking that they really want you to be doing on the AP exam. So this is a multiple choice PES. All right, now here's the thing. Here's my question for you. There are 2 elements represented here. So peak X is one of the elements and peak Y is the other. One of the elements is fluorine and one of the elements is carbon. So notice, this is not a graph of 1s, 2s, whatever. They've labeled it 1s for each one. So we're talking about the same electrons. And this is exactly what we were doing back here. We're talking about the 1s electrons. So what I want to know, if one of those peaks is carbon and one of those peaks is fluorine, then which one do you think is peak X? You can type in your answer. Do you think that PX is fluorine or carbon? All right, y'all are coming in so far so good? So if we look at the periodic table, and remember, you have this in front of you on test, you have this in front of you for the AP exam. Don't be afraid to use your tools. Carbon, according to the periodic table, has 6 protons, and fluorine has 9 protons. So the question is, who do you think is going to have a stronger pull on those electrons? Carbon or fluorine? Well, fluorine has more protons, just like one of y'all said, and because it has more protons, it pulls harder. So really, this peak here at 70 would be fluorine. So peak X is fluorine. Peak Y would be carbon, and the reason for that is because there's just more protons. Now, we get fancy sometimes, and we call that a greater effective nuclear charge. That's just a fancy way of saying it has more protons pulling on the electrons. But notice how it's really easy to get messed up with this graph because, again, it starts at 80 and ends up at 0. So you may look at peak Y and say, oh, that's a greater number, while over here, peak X actually has a greater ionization energy. So the height of the peak, notice it says intensity. That doesn't mean the number of electrons. It just means how strong of a signal it was given off. So it's kind of like COVID. You can either have a lot of COVID virus in your body or just a little. That's the difference in the heights. So let's keep going, see how we do. So what are the periodic trends? And you may remember this from regular chemistry, but there's a thing called radius. Now, you may have learned atomic radius and ionic radius. And I'm here to tell you they're the same thing, right? Ionic radius is the radius of an ion, and atomic radius is the radius of just an atom. So remember, ions are things that are gained or lost electrons. And on the AP exam, you might be asked to compare the size of an ion to the size of an atom. So that's why I made it just radius. How fat or how big is that atom or ion? Ionization energy is just what we were talking about with PES. How much energy does it take to remove that electron? Electronegativity is how much energy, electronegativity is how much an atom pulls on the electrons in a bond. So when you compare two things, if you remember doing electron dot structures, you kind of get the idea of, is one thing pulling on the electrons more than another? And if they did, we called that a polar bond. And so electronegativity is the idea of who has a greater electronegativity. And we judge that based on a couple different criteria, but oftentimes we still talk about where are the electrons at, those valence electrons, the outermost, and how many protons does something have. Electron affinity is another one that me personally, I don't see a reason for, because if ionization energy is how much energy is absorbed to make an electron knocked off, then electron affinity is kind of a measure of how much energy is released when an electron is added. So think of ionization energy as electrons being knocked off, and electron affinity, it means as you add an electron to something, how much energy is released. So this is something that if you're using the student notes from A+ College Ready, and if not, ask your teacher why not, but they're there for you. So when you answer periodic trends, it's very, very important to talk about both of the atoms. If it asks you to compare things, you don't want to say just carbon, when really you meant to say carbon and fluorine. You can say, oh, by the way, electronegativity goes over to the right and up, and you would be right, but that is not really testing your knowledge. Do you understand why electronegativity increases as you go up to the top of the periodic table and over to the right? So remember, you're always looking to state the explanation. We're going to refer to Coulomb's law as much as possible. And we're going to talk about the energy or forces of attraction and repulsion. So just like y'all did before, you were talking about it has more protons, and the protons have a greater force of attraction for those electrons. So you're always trying to use those words as you go. Some of y'all may or may not remember Coulomb's law, and Coulomb's law is pretty straightforward. Don't worry about the K part. You'll never actually calculate anything, but it's Q1, Q2 over R squared is the force. And what we can say is Q1 is usually the charge of a positive thing. So maybe you have 7 protons. That would be a +7 charge. Q2 is typically the charge of the negative thing. So you might have 7 electrons. So that would be Q2, would be 7 negative charge. And then the R squared is just the radius. And we need to talk about that in terms of how far away something is. So when we talk about the 1s electrons, those are really close. But then when we talk about the second energy level, those electrons are farther away. So we're either going to worry about Q1, Q2, so how many protons it has and how many electrons, or we're going to worry about the radius. At this point in your life for the AP exam, you really won't ask them to say, talk about both, right? Just remember that mathematically, if you put a bigger number in for radius into the denominator, if you put a big number down there, you're going to get an overall smaller answer for F. So the farther away you are, the less the force of attraction. And if you look on my screen real quick, I'm just going to show you that real quick. If you change the positive negative to +10, -10, there's a greater force of attraction. The closer together you get them, the greater the force of attraction. And the farther away they get from each other, the smaller and smaller the force of attraction. If you understand that, then you're good to go, right? So we can either talk about charge or we can talk about distance, but it rarely will have you talk about both. All right, so we're going to cover this question. Predict which element has a greater ionization energy. Now, you can drag the blue icon that you see, that blue arrow. You can drag that icon over which element you think will have a greater ionization energy. I gave you a piece of the periodic table for you, but feel free to look on your own and drag the blue diamond into which one you think would have a greater ionization energy, sulfur or argon. Oh, can y'all just drag them on top of the words sulfur or argon, not on the periodic table? Sorry. Sorry, that's me. So you can just drag it over to sulfur in the line that I typed, or you can type it over the argon. Okay. Y'all were straight up going down the periodic table, which is my fault. That's what I get for giving y'all lousy instructions sometimes, but that's good. All right, so let's see what y'all came up with. I'm going to go ahead and show you what y'all's answers were. And you'll notice most of you, well, there's the one person. Most of y'all picked argon over sulfur. So let's get into maybe why that is, right? So remember that when we do this, we need to talk about mentioning both the atoms when we're explaining something, not just one of them, but we want to really attempt to explain the why. And if we can talk about Coulomb's law, we always sound so much smarter, right? So when you do one of these and you're going to have to basically explain your answer, here's what it wants you to do. It wants you to predict. Well, that's what you already did, right? You made a claim or a prediction by dragging it. So you would pick one of those two. Sometimes on the AP exam, they will give you the pick. So they'll say argon has a greater ionization energy than sulfur, right? They'll give you that. Or sometimes they could give you a graph of PES and say, why is the peak of 1S a greater number for argon than it is for sulfur? They're all the same thing. Make a prediction, or they give you a prediction. Or sometimes they'll say, a student named so-and-so predicts that sulfur has a greater ionization energy. And then it says, do you agree or disagree? And this is your claim or your prediction, is you're agreeing or disagreeing with what they say. So you need data. So what is the data that we always use to prove this? Well, it's all about protons and electrons. So our data is going to be the electron configuration for sulfur and the electron configuration for argon. And let's go ahead and include in that the number of protons for sulfur and the number of protons for argon. So this is what the data looks like. Now, I chose to give you the noble gas configuration because, after all, I'm a lazy person. But sometimes it'll ask you for the electron configuration. Sometimes it might say, you can give me the noble gas configuration. Or sometimes it might say, just give me the valence electrons. And remember, those are the electrons in the outermost energy level. So the only thing you would write over here would be 3s2, 3p4, right? So that would be the data. Notice, I'm not giving any opinion. I'm not saying anything like that. And what I want you to avoid when you're giving data is I want you to avoid saying argon is farther over to the right or argon is farther up the periodic table. That is correlation, not causation. Meaning, yes, it's true, but that being farther over to the right has nothing to do with what we're talking about. So don't worry about, oh, well, sulfur needs 2 electrons to give it a completely filled shell, and argon needs none. That's a true statement. I have no problem with what you're saying. I do want you to think about, though, number of protons and number of electrons, because it's the protons who attract the electrons. And it doesn't matter what periodic trend you're talking about, pulling on the cloud of electrons or ionization energy or electronegativity, it's all about protons and electrons. So what would the data look like that supports the prediction? The data we have here. How would you explain the data? So your explanation would look something like this. Now, you really want to take your time as you answer these questions and make sure you know, you're telling the person reading your answer that you're really smart and you totally got this. So the data's there, you're not giving any opinions, and then your explanation would be that they have the same number of occupied energy levels. They both have electrons in the 3rd energy level. So radius is not important because they're both electrons in the 3rd energy level. If one had been in the 3rd energy level and one in the 4th energy level, then we would worry about radius. So any time that the electrons are the same distance from the nucleus, then you're going to be talking about protons. So argon has more protons, and more protons means a greater pull on the electrons. And then more pull means it takes more energy to remove the electrons. Now, I also could have talked about Coulomb's law. I could have said that the force of attraction is a function of Q1, Q2. And because argon has a greater Q1, Q2, 18 protons versus 16 protons, then that would mean that it has a greater pull on the electrons. But notice I'm talking about both elements, argon and sulfur. I'm talking about the data that I wrote down, and then I'm describing why that's important. Has more protons, protons pull on electrons. More pull means it takes more energy. Leaving out any part of this would probably mean you don't earn the point. If you just said argon has more protons, that's true. They're asking you to make that one more connection. Can you connect the idea that more pull means a greater ionization energy, because more pull means it takes more energy to remove them? So that's the kind of thing you're going to want to frame your answers in. All right, so here's an application time. I know it's kind of fuzzy on your screen, and I apologize. This is a question that was asked several years ago. This was an FRQ. So it combines everything that we've kind of been doing so far today. So could you write the ground state electron configuration of the iron with a +2 charge? So what does it mean to have a +2 charge? Well, iron typically has 26 electrons and 26 protons. So in order to have a +2 charge, that means it's lost 2 electrons. So iron would only have 24 electrons. So if you wrote the electron configuration for iron, it would be 1s2, 2s2, blah, blah, blah. And then it would say 4s2, 3d6. So the question comes up, if you're talking about the iron ion, what electrons would it lose? Well, it always loses the valence electrons first. So look at the periodic table on my screen. Which electrons, 4s2, 3d6, which electrons are the outermost electrons? Those outermost electrons are these 4s electrons right here. So those are the ones we're going to lose. So if iron loses 2 electrons, it loses the 4s electrons. So you would just write the electron configuration, but you would leave out the 4s electrons. And that's something that you can practice and is relatively easier. Then it gives you a data table, and it says the radius of each one is given. Using principles of atomic structure, explain why the radius of the Fe2 ion is larger than the radius of the Fe3 ion. And there's all kinds of answers you could give to this, but the Fe2 and the Fe3 basically comes down to the Fe3 plus has the same number of protons pulling on less electrons, is a good way to kind of put that for right this moment. And because there's more protons, the same number of protons pulling on less electrons, you kind of get a greater force of attraction, meaning it kind of shrinks the electrons down. And then part C, it interacts more strongly with water molecules than iron ions do. Notice that this talks about Coulomb's law. Coulomb's law can be used not just for protons and neutrons. Coulomb's law also comes into something called intermolecular forces that you'll see in Unit 3. But for right now, just notice that Coulomb's law comes up. And notice that their questions are really asking you to synthesize electron configurations, how one has something to do with the other, and so on. You can see there that those are the answers that you would expect. And don't worry about this bottom part. That will come back to you for part C down there when you talk about intermolecular forces. But just notice that that knowledge of Coulomb's law is very, very important. So here's another one. This was taken from a couple years ago. So every part before this, part E, so A through D was talking about a battery, which is way later. That's like Unit 9. But notice that they did throw in a part in here where they said, write the electron configuration for a zinc atom in the ground state. And ground state means just all the electrons where they should be, right? So you would go over to your periodic table. You would look up and say, oh, zinc has 30 electrons. And so I would start and I would go 1s2, 2s2, 2p6, 3s2, blah, blah, blah. And so you would get the electron configuration. That's worth a point. From what sublevel are electrons removed when a zinc atom is oxidized? So that requires a little bit of knowledge. Oxidation means losing electrons. And which sublevel are they removed? They're talking about the 2s or the 2p, the 4s, the 3d. That's what they want you to ask. And again, it's asking you to go, you always lose those valence electrons first. Notice the second question that they kind of give you. They give you the isotope and its mass, and they want you to calculate the percent abundance of each isotope. So notice how before they gave you percentages and you went and found the average atomic mass. In this one, they're giving you the average atomic mass, and they know that this is the mass of each isotope. And the way you're going to do this is if you say neon 20 is element X and neon 22 is Y, and the X and Y represent the percentages, you can set up a system of equations or substitution where you solve for X and Y. And I'm sure your teachers will be doing that with you in the coming days. They also could have been asking this question in terms of, here's a graph, and can you find the average atomic mass? So they could have given us a spectrogram where you were reading it and trying to figure out what you know. And then that very last one, what I want you to notice is that part about a mole that we talked about last week. Calculate the number of neon 22 atoms in a 12.55 grams. That's simply asking you to go from grams of something to atoms of something using that concept of a mole. So in order to solve this, you would go to your knowledge base and you would look on your sheet and you say, oh, I know that 1 mole is 20.18 because that gave it to you in the problem. And then you know that 1 mole is 6.022 times 10 to the 23rd atoms of it. But here's what I want you to notice. This is why this is a great question. This was asked just a couple years ago. You get 1 point for using the correct molar mass. So just plugging in this number and showing your work, boom, you get a point. You get 1 point for knowing that the neon 22 was 0.095. And you know that because, sorry, that was totally mine. I just screwed everything up. Hang on. So sorry. Okay. And you know that because you did the work for letter A, subpart I, where you calculated the percent abundance. So you found percents. So the point here is, if you use that data here and you plugged in your percentage, then you could very well earn a point. So this is out of a 10-point question. You can pick up 3 points just for knowing the mole concept, right? So we really want y'all to be very knowledgeable. So 3 things that we did today. We talked about periodic trends, all about protons and electrons, but you have to know where the electrons are and how far away they are, and we get that from electron configurations. And then we also need to know the number of protons, which you can find from the periodic table. And then how to read a mass spec graph, and then how to read a graph about a PES, right? So if any of those things bothered you today, ask your teacher to go over them as y'all go over Unit 1. And there's lots of examples and stuff included in the A+ College Ready resources. So with that, I'm done. So we can go ahead and I can stick around and answer any questions that you guys have. Otherwise, thank you guys so much for coming today. And I hope y'all have a great week.